3. Introducing the notion of estimation. In a real-life situation, you measure some quantitative variable on a sample of size n, in order to estimate the mean mu of what you measure. Formally, you would say that you observe a bunch of random variables xi that follow a normal distribution with mean mu and variance sigma square. From the realizations, you usually want to estimate mu, to get some insights on your population. To do so, you use an estimator of mu, usually x bar index n, which is equal to 1 divided by n, and multiplied by the sum of the xi. Why would you do that? The answer is, x bar index n has some very good properties. This estimator is a random variable which expectation is equal to mu. By definition, in probability theory, the expected value of a random variable is intuitively the long-run average value of repetitions of the experiment it represents. The other very important property is that the distribution of the mean x bar index n is approximately a normal distribution, whatever the original distribution of the xi. It's incredible but true. The thing is, in a real-life situation, you only have one sample, in most cases. But if you had the possibility to have an infinite number of samples, you would be able to calculate an infinite number of means and to calculate the mean of the means. From that, you would get the expectation of x bar index n, as well as the standard deviation of x bar index n, and its distribution. You would be able to get a confidence interval of the mean, which is really important. 3.1. The very important concept of sampling distribution. 3.1.1. The mean of the means. If you had enough money to run several times the same experiment, and hence to have measures from many different samples, you would see that the mean of the means over the samples is equal to mu. Practically, it means that estimating the mean by using the formula 1 divided by n multiplied by the sum of the xi, that you've learned when you were in school, is a good thing to do. This estimator has a very good property. 3.1.2. The variance of the means. Remember the previous graphical representation that you obtained from 11 samples. The means that you have calculated for the 11 samples are not exactly the same. They vary, but not as much as the original data. It's not only important to understand that, but it should be also very intuitive for you. When the population is infinite, and in the case of withdrawals with replacement, the variance of x bar index n is obtained by the following formula. Why so? It should make sense for you that the variance of x bar index n depends on the variance of the original data, the ones that you measured on your statistical individuals. If the data are variable, the average will certainly vary from one sample to the other. To understand the denominator, let's take samples of different sizes. If you measure small samples, the mean of your samples will vary more from one sample to the other than if you measure large samples. Let's take samples of size n equal to 2 for instance, which is really unrealistic. In one sample you may get 2 small individuals or 2 big individuals, which can explain the fact that the mean may vary a lot from one sample to the other. If you work with samples of size n equal to 10 million, which can also be unrealistic, you won't probably get 10 million small individuals in one sample. For these samples of large size you will probably have something representative of the distribution of your individuals. The means over something representative will not vary a lot from one sample to the other, as they are all supposed to be representative. This result on the variance of x bar index n is really important. I'm sure that you have already seen this formula somewhere, and each time you want to calculate a confidence interval for some estimator, you divide some variance by the square root of n. Don't do that systematically. You have to understand what you're doing. If you are interested into some kind of estimator, all you have to do is to get the variance of that estimator. If your estimator is blah blah, you need to know the variance of blah blah, in order to get a confidence interval for blah blah. 3.1.3. The distribution of the means. The way x bar index n is distributed is not dependent from the fact that the xi follow a normal distribution. This result is not that intuitive, but it is really important, as even though you're not working with normal distributions, the estimator of the mean will follow a normal distribution. That's the central limit theorem. What if the real distribution is not a normal distribution? Let's take an example based on a chi-square distribution, and let's have a look at the following exercise.